Welcome learners. In today's lecture, we are going to start the third chapter from our main textbook by William Hayth and John Buck. This is the ninth edition of Engineering Electromagnetics book. In this chapter, we are going to start discussing the principle given by Faraday's law on what happens to electric charges when they integrate or they interact with insulating materials. Then we are going to look into the phenomena experimentally proven by Faraday known as electric flux, and then what happens if all the flux lines are combined together, so we term them as electric flux density. So in the previous chapter we talked about the concept of streamlines. So what are streamlines? So streamlines basically gave us the direction of force that was applied on a test charge at every point. So if I had a test charge, let's say Q naught, and whatever the force was being applied from all the directions, we termed them as the force or streamlines being applied. Now in this chapter, let us give a proper physical significance to these lines or vector directions applied on a test charge, and we say that these lines are basically the flux lines. There are other names associated in various books which for streamlines, and sometimes they are known as direction of or directional lines. Sometimes, so this is one way to represent these streamlines. The second way is field lines. So they are referred to field lines as well. Then they are referred as lines of force around a charge. They are also known as electric flux lines and also called as displacement lines or sometimes electric displacement lines. So these are the different names associated with streamlines, which are basically the arrowheads or the directions showing us how much the lines are moving to a certain test charge. In this course of electromagnetic field theory, we are going to name these lines as flux lines or electric flux lines. So our analysis will be on electric flux lines, which basically tell us that where are the lines moving towards. So these lines, even if originating from any test charge, are known as electric flux lines. Another thing associated with electric flux lines is that electric field and electric flux density. So previously we talked about the field lines and what was the field lines about. So we understood the concept of electric field intensity. This is represented by the symbol with an arrowhead as it's a vector quantity as E. Now the other quantity that is associated with field lines is called electric flux density. Again, it's a vector quantity and represented by symbol D with an arrowhead. So whenever we talk about field lines, we have to keep in mind that electric field intensity and electric flux density always go side by side. So these are the two parameters associated with field lines. So what's the similarity and the comparison between two? So both the lines are related to each other as they are almost parallel to each other. So the word here is almost. So how almost we are going to look, but mathematically the electric flux density and the electric field intensity are associated by this mathematical expression, where you can see that they are almost parallel or directly proportional depending upon what is the material. So here epsilon naught is the property of any material. If you're talking about air, the value of E naught comes out to be 1. If you're talking about vacuum, the value of epsilon naught comes out to be 8.85 into 10 raised to power minus 12 farads per meter. So you again see that it is going to be the value of permittivity or epsilon naught that is going to decide whether D and E are almost alike or they are different. What is the scenario where these two fields can be different? If the material property is different. For example, in your lower classes, you might have heard about how a light propagates from one medium to another. For example, if this medium is air and other is water. Now, if the light is incident or traveling in the air, so this is my incident ray. And what happens when it moves from one medium, we call this as E1, and move it in the second medium, water, we experience the law of refraction. So again, in this scenario, the value of E and D or the rays are not alike, rather there are difference in terms of its angle. It can be 90-degree apart or some different angle, but they are not always parallel. So this is what it means, that the property of the material decides whether E or D are alike, proportional or parallel or not. So how can we understand the difference between an E field and a D field? So we can say that E field or electric field intensity acts as a force field, and electric flux density D, which is always going to exist whenever we have E, is basically acting as a source field. So this is the easiest way to understand them, which means that E basically tells us, E is going to tell us that how much force a charge will experience or will feel. On the other hand, electric flux density basically tells us how much charge is producing the field. So you can see that both go hand in hand. So this is the comparison between E and D. And I remember that both E and D are vector quantities because they are associated with a direction and a specific magnitude. Another way to understand D and E is if you consider the analogy of a water tank. So if this is your tank of water and this is the outlet connected with the tap over here. So D is basically all the amount of water stored inside the tank because it's a source field. It is measuring of how much water is inside the tank. And E field on the other hand is basically telling us, or it is measuring how much strength the water will flow with at a certain point. Again, depending, if I open the tap slowly, the water will move with a less strength. If I move it quickly, or if I open it completely, then the strength of the water will be very fast. So this is the strength of the water waves or the fields in our case associated with electric field intensity, and D is associated with the storage of charges, or in this example, how much water is inside the tank. So this is the relationship between electric field intensity and electric flux density, and the main equation that governs the relationship is shown over here by equation number 1. We are going to prove this equation as well, but again this is the comparison between D and E. So now let us come to our first experiment that was done by Faraday when he was serving as a director of Royal Society in Britain, and in the year 1837 he was thinking on a problem for almost a decade. And the problem was that what happens to the electrostatic charges if they are interacted with insulating materials? What is going to be the effect on those static fields by these materials? So in order to do the analysis, he prepared an experimental setup in which he took two concentric metallic spheres. One was a small sphere which he termed as inner sphere, and one was a larger hollow sphere which he called it as an outer shell. And in between these two shells he inputted various kinds of insulating or dielectric materials that were about 2 centimeter apart. So as you can see in your image in the bottom right, this is the inner sphere, a smaller one, and this is the outer sphere over here, and you can see it's an empty shell from the inside the outer sphere, and both these outer sphere were clamped together. So this is one portion of the outer sphere, this is the other portion of the outer sphere, and they both were connected or joined together, where inside was this small inner sphere. So his experiment basically was that initially he charged the inner sphere, let's say with positive charges, by rubbing it with a material like glass, paper or wool, and then the outer sphere was assembled or clamped together, and since it was a conducting material, the outer sphere was electrically neutral, so he basically made the outside of the outer sphere as charge free by connecting it to the ground, and then he measured how much charges were available on the inside of the outer sphere, and this was his whole experiment. So in order to put it into simple words, we can see the cross-sectional view of the inner and outer sphere. So this is my inner sphere which he experimented with. It is positively charged with Q charges. Then he placed an outer sphere which was hollow from the inside. So this is the let us say inside portion of the outer sphere, and this is the outside portion of the outer sphere. Since by law and naturally an conducting metal is electrically neutral, which means that it is going to have equal number of negative charges and equal number of positive charges. So the outer shell or sphere had inside and out electrically neutral property, which means that the charges were equal. The next step he did is he removed the positive charges from the outside of the outer shell by connecting it to the ground. So all the positive charges over here, they were negated by connecting them to the ground. And then he measured that how much charge was available on the inside of the outer shell. So if this is the inside of the outer shell, obviously he opened the apparatus and he found that whatever charge was present on the inner sphere, let's say in this example, in this scenario, the inner charge was charged with positive Q charges. The same amount of charges in magnitude were available on the inner side of the outer shell, but with a negative sign. So this is the observation he presented. He said that the charges of the inner and outer sphere were having equal magnitude, but the sign was different regardless of insulating material. So whatever was in between these two spheres, any insulating material, the charges always had the same magnitude but were in opposite in sign. So let's take a clear picture of this. So initially he charged the inner sphere with the positive charges. So you know that if any object is charged with the same charge element, by Coulomb repulsion, all these charges are going to repel each other and they will go to the surface of the sphere. So all these charges is going to push each other out such that they go out the outer sphere. So this is how the charges moved on the outside of the inner sphere. So this is the inner sphere that was made positively charged. Then he introduced the inner sphere with the outer shell. Inside was the dielectric medium like a foam, rubber, or piece of wood or plastic. Then in the outer sphere, as I mentioned earlier, it is electrically neutral, which means it had a positive charge and the negative charge on the inside and outside of the outer shell. So he connected the outer side of the shell to a ground so that all the Q charges are terminated or they cancel out, or the effect was cancelled out. And then later on he measured what was available on the outside shell, and it was all the negative charges which were lying inside. Since they were all of the same charge, they repelled each other and came on the outside of the shell. So finally he concluded that whatever was available inside in the form of charges on the inner shell, the same amount of charge in magnitude is going to appear on the inside of the outer shell, but with a negative sign. So this is the experiment that Faraday gave, and thus he presented all these analyses saying that there was some kind of force that were directing the charges from the inside to the outside, and he called all these as an electric flux. So this was the displacement of charges from the inner shell to the outer shell. So the inner charge was Q plus Q and the outer had a negative Q. So the movement of charges from the inside and outside, he gave them a name which was an electric flux with the symbol psi, and it was equal to the total amount of charge on the inside shell, which was Q in this scenario. So this is the experimental observation and analysis done by Faraday's law, and obviously the equation came out to be that the electric flux with the symbol psi is equal to the total amount of charge present inside of the inner shell, and its unit in SI unit was coulombs, represented by C. So this is what is known as an electric flux. So similarly, we can further go and see what happens if we have more flux lines. So again, flux is now represented as one flux line is equal to 1 coulomb of charge. So this is a single flux line originating from this charge of Q. This is a second flux line, a third line, and all these are 1 coulomb of energy of charges. Now what happens if I combine all these lines and represent it by a single quantity? So I can say that the charge is giving one major flux density. So that is now termed as electric flux density. So our next topic is what happens if we combine all these flux lines and see their effect on a single point in space. So we term those combination of lines or electric flux as a electric flux density, represented by symbol D. So you can see that all these flux lines are moving through this surface and they are crossing the surface in space towards this direction. So these are all electric flux lines, and if I want to see the effect at this point, I can say what is the electric flux density at this point. So let us figure out the mathematical expression for electric flux density. So we can say that if I have a charge Q, let's say I have a charge Q on the inner sphere, and now I know that the charge is going to radiate in 3D space uniformly. So these are the electric flux line. Now I introduce another outer sphere around this charge. Let us say the radius of this sphere is A. So the field lines are going to pass these new radius or outer sphere with radius A. So I can say that the equation for a charge or a point charge is going to be in terms of electric flux density, because I want to know the effect of all these lines at a single point in space. So I'm represented by electric flux density with the symbol D. So the density is equal to the total amount of electric flux per unit the area of a sphere, and the area of a sphere is 4 pi r square. I know that according to Faraday's law, this electric flux is equal to the total charge present inside per unit the area of the sphere, which is 4 pi r square. Since the area is now represented by a value A, so I can write this as charge per unit area in terms of 4 pi A square. So since this is now a scalar quantity, I want to convert it into a vector representation. So I am going to write the unit vector in terms of A of r. So this is the equation for the electric flux density passing through the outer radius or sphere of radius A, and its unit is coulomb per meter square. Similarly, if I introduce another radius outside of this, let me call this as r equals to v. Since the radius is increased, the area also gets increased. So electric flux density for the second scenario comes out to be charge per 4 pi b square A of r. So finally, a generalized form for charge electric flux density comes out to be the electric flux density is equal to charge per unit sphere in this direction. So this is the equation for the electrical flux density, or the generalized equation of the electric flux density. Now what happens if I start to shrink the inner sphere that had this charge plus Q? So let's say if I had this charge plus Q, it meant that it had a lot of positive charges, and due to repulsion it came on the outside of the surface, and thus the electric fields started to move from these charges. So this was the scenario that we built. Now what happens if I start squeezing or compressing this? It means that my space is going to become so narrow that I'll be left with only one point charge. So what is the electric field of a point charge? So electric field of a point charge is basically Q divided by 4 pi epsilon into r square into A of r if it's a vector quantity. So now we can see there is some similarity between the electric field and electric flux density. And again, if we do the comparison of these equations, we get our base equation of relationship between electric flux density and electric field intensity, and it comes out to be D equals to epsilon E. So this is why we say that whenever an electric field exists or electric field intensity exists, then electric flux density is also going to be available. In this case, this is for a point charge. But if the thing or these relationships exist for a point charge, this means that D and E relationship is also going to exist. So we can say that the relationship between electric field intensity and electric flux density is also going to exist for which things? For line charge distribution, similarly for volume charge distribution, and similarly for surface charge distribution. So which means that if I want to write the electric field equation for all these charges and then its corresponding electric flux equation, it is going to be as such. So we know that the electric field intensity for the line charge distribution is rho of L divided by 2 pi epsilon into absolute of rho. If it's a vector, then it is A of rho. Similarly, for volume charge density, it is going to be integral of volume rho v dv divided by 4 pi epsilon into r square if it's a unit vector A of r. Then for the surface charge density, it is going to be rho of s divided by 2 epsilon into a normal vector. This means that the electric flux density for these three equations comes out to be, for line charge, for volume charge, and for surface charge, is going to be the same representation without the value of material property epsilon, because this is going to cancel out. So electric flux density for line charge distribution comes out to be 2 pi into rho, and for to make it a vector I'm going to use the arrow. Then for volume charge density, it comes out to be integral of volume rho v dv divided by 4 pi r square into A of r. And then for space charge density, it comes out to be rho of s divided by 2 into normal vector A of n. So these are the relationship equations between electric field intensity and electric flux density in terms of point charge, line charge, volume charge, and surface charge distribution. So now let us understand the problems associated with these charge densities, or especially the electric flux density and finding the electric flux. So in this first question, we have been asked that we are given a charge of 60 microcoulomb that is located at the origin, and we are asked to find the total electric flux passing through. First point A is when the sphere has a radius of 26 centimeter bounded by the range of theta and phi. In the second part, it is a closed surface with the value of rho as 26 centimeter and z is in the range of plus minus 26 centimeter, and in the final part, the plane z is at 26 centimeter. So let us first try to solve the first part. So first we have to visualize this, and let us say where our charge is. So let me draw the right-handed xyz coordinates and then give the respective axis for the spherical coordinate system, because we know that this is a sphere because the ranges are given as r, theta, and phi, and we know that the charge is at the origin. So our charge is 60 microcoulomb and it is placed at this origin. Now we know that the spherical coordinate system is having this structure. So let me complete this. And we know that this portion here represents theta, this movement from x to y is phi, and then value of r comes out to be this one. So that is 26 centimeter. Okay, now we know that the value of r is between 0 to 26 centimeter. Theta is now from 0 to pi by 2 and phi is from again 0 to pi by 2. So this means that we have to find the effect of this charge q in the form of electric flux. So we need to find electric flux. So electric flux is equal to the total charge enclosed. Now we already know the charge enclosed is 60 microcoulomb, but how much charge is enclosed inside this sphere? This is what we need to figure out first. So in order to figure this out, let us see which region of spherical coordinate systems we want to do the analysis on. So we know that the region of theta and phi is not having its complete range, rather it is 1/8 of the portion. How can we figure out that this is 1/8 of the sphere? So the fraction of the sphere, to figure out fraction of the sphere where the charge is going to radiate its electric flux lines, let's say it's going to be ratio of the theta range provided by the total range. So theta normally is from 0 to pi, then the phi range which is given to us divided by the total range. So phi covers the azimuthal range from 0 to 2 pi. So if I incorporate the values, theta range is given to be pi by 2 divided by pi multiplied by pi by 2 divided by 2 pi. So this goes over here and this goes to the denominator, and then it is going to cancel out. So I'm left with 1 by 2 multiplied by this, and this will cancel out when it goes up. So it is going to be 1 by 4. So we can see it is the 1/8 of the sphere, which means this is the portion I'm getting from for theta to be pi by 2, and this is the region which I'm getting for phi equals to pi by 2. So now I want to know in this range how much energy the charge is radiating in terms of the electric flux. So we already know that electric flux is equal to the total charge q. Since this is 1/8 of the portion, so the total charge will be divided by a fraction of 8, and it comes out to be 7.5 microcoulomb. So this is the amount of electric flux that is being radiated in this specific portion of the sphere, and you can see the answer is also shown over here. So this was the solution to the first part. Now let us go to the second part and see what we can do for the second part. So in the second part, I'll use this space. We have to work with the cylindrical coordinate system because the x's are rho and z. So let us draw the cylindrical coordinate systems. Again, starting with the right hand rule, if this is my y, this is x, and this is z. So I know that the cylindrical coordinate system will have a value of phi. Let's say if z is at plus minus 26, so my cylinder will be something like this. This is the point I'm getting. My charge is again at the center, so this is q, 60 microcoulomb. Point of rho is something like this, and if I move from x to y, this becomes phi, and then I move in the z direction, it is 26 centimeter over here, and it is negative 26 centimeter over. So I can see that my charge is inside the complete cylinder, which means whatever the electric field lines are going to be generated, it is going to be confined inside this cylinder. So the total electric flux is going to be whatever is the total charge at the origin, and it comes out to be 60 microcoulomb. So this is the answer to the second part. Nothing is going to be changed over here because the charge is at the origin and it is confined inside the complete cylinder, because the range of the cylinder is phi is between 0 to 26, and the value of phi is from 0 to 2 pi, and the value of z was between minus 26 to plus 26 centimeters. So because of these ranges, everything is confined, or the charge electric flux lines are confined inside this cylinder. Finally, in the third part, we have to work and see if the plane is at z equals to 26 centimeter. So for the third part, let us draw the coordinate systems. This is now a rectangular coordinate system. This is z, this is y, this is x. Our charge is at the origin, so q is equal to 60 microcoulomb. Now we want to see where the field lines are going. Since it is asking us the plane for z is equal to 26 centimeter, so which means that our plane, let's say if I assume this is something like a 26 centimeter, then the z-axis plane along y and x parallel is going to be something like this. So this means that the minus 26 charge or the plane could be over here if this is minus 26 centimeter for z and this is plus 26 meter. So I can assume this is basically a visualization and there is no mathematical association. I want to find electric flux which is equal to the total charge, but in this case I know that half of the energy radiated in the form of electric flux lines will move to the positive z-axis which is at 26, and the remaining half, because of uniformity, will move to the negative side. Since we are not interested in the negative z-axis, which means only half of the energy will be radiated in the form of electric flux lines, so the total electric flux lines will be 30 microcoulomb. So we can verify that the total flux lines will be 30 microcoulomb because only half of the lines are propagating in the upward direction at 26 centimeter for the z-axis. So this is the solution to the third part of the problem. Let us now go to another problem and see what else we can find. Till now we have seen how to find electric flux. Now let us move to finding electric flux density. So in this problem we have to calculate D, which is the electric flux density for a rectangular coordinate system point at 2 minus 3 6, and the point of concern is this one. So this is basically the test charge where we want to do the analysis or where we want to find the electric flux density. In the first part, the source is a point charge of 55 millicoulomb and it is located at point Q. In the second, source is a uniform line charge with 20 meter coulomb per meter on the x-axis. So this is important. And in the third part, we have the source as a uniform surface charge density on the plane of z equals to minus 5 meters. So let us start with the solution of the first part. So the source point is, let's say we call this Q of A, and it is at point, let us say I say it is at point minus 2, 3 and minus 6, and the point or the test charge is located at point P, that is 2, minus 3 and 6. Now I need to find the electric flux density for this point charge scenario. So I know that the electric flux density for a point charge is Q divided by 4 pi r square into A of r. This r square, let us say, is the distance between P and A. So this is the distance vector, and obviously the unit vector is also going to be P and A. So I can replace this as Q divided by 4 pi r square PA into r PA unit vector. So now let us first find the value of this unit vector r PA. Let us take this. So we know this is the difference of this with this vector. So it comes out to be 2 minus minus 2 along A of x plus minus 3 minus 3 A of y plus 6 minus minus 6 A of z. So the value of the distance vector comes out to be 2 plus 2 is 4 along A of x, then minus 3 is minus 6 A of y, and then it comes out to be plus 12 A of z. So this is the distance vector between point P and the source, which is a point charge at Q. So I can find the magnitude of this unit vector because I need to solve for the unit vector as well. So the magnitude is just square of the scalar terms. So this is 4 square minus 6 square, and so you can say 12 square. It comes out to be 14. So this is the value. This means my distance, the unit vector P of A, let's say, is basically r P of A divided by the absolute of P of A. So this is going to be 4A of x minus 6A of y plus 12A of z divided by 14. So now as I have everything, I can incorporate everything into equation A to find the electric flux density. So electric flux density is going to be the value of Q, which is 55 into 10 raised to power minus 3 coulomb, divided by 4 pi, and R is the square, so it comes out to be 14. You take the square and you put the value of unit vector, which is this one, so it comes out to be 4ax minus 6ay plus 12az divided by 14. So once you solve this, the answer comes out to be electric flux density is 6.838 a of x minus 9.57 a of y plus 19.14 a of z. The unit is microcoulomb per meter square. So this is the answer you should be getting, and we can confirm the answer from section A over here. So this was the solution to the first part of this problem. Now let us look at the second part. In the second part, the test charge remains at the same point P, but now the source is a uniform line charge or line charge distribution along the x-axis. So let us go to the second part, and it's a uniform line charge distribution along the x-axis. So and value of line charge distribution is 20 millicoulomb per meter cube. Okay, so let us draw this and see what we can get from here. Let me put this space so that we can do the third part over here. So if I draw this again, I'll make my axis. So this is y, this is x, and this is z. This is the origin, and the line is along the x-axis. So let me draw the line with a different color so this becomes clear. So the line or the line charge distribution is on the x-axis. So this is the line charge distribution, which means that it is having all the source charges, and the value of this is rho of L, which is 20 millicoulomb per meter. So, and the point of interest where we want to find this is basically P 2 minus 3 and 6. So if it is 2 minus 3, it is going to be somewhere over here. So this is point P at 2 minus 3 over 6. So again, if you remember, whenever we deal with problems associated with line charge distribution, we always draw a perpendicular originating from the line. So if this is a line, this is a point, so we always draw a perpendicular line moving from the source to point P, as it makes an angle of 90 degree, and this is basically our distance vector RAP, or you can call it as rho AP. Later on we can change that. So now we need to find the equation for the electric flux density. So electric flux density for the line charge distribution comes out to be rho of L divided by 2 pi absolute of rho and then the unit vector A of rho. So this R of rho can be R rho as well, because the radius and the values of the rho are the same. So now we need to find rho. So let us first start finding the value of rho, which we called as Ra of P, the distance vector. So it is going to be the difference between the source point to the target point P. Now what is the source point? We need to find the source point, let's say A over here. So the source point, whenever dealing with the line charge distribution, we want to see where the line is formed. Now the line is along the x-axis, so it means that the first value of x will be the same value which is for the point P, because the difference comes out to be 0, and the remaining axis will be 0, 0. So this is the point or the distance we got. So this means that the vector r is going to be r of P minus r of A. So it comes out to be 2 minus 2, so it is automatically 0. Then you have minus 3 with 0 is A of y, and then you have plus 6 A of z. So this is the rho or the distance vector that we got. Obviously, if you take the magnitude of this vector, so it is going to be the square of the scalar terms, which is minus 3 square plus 6 square, and you will get the value of here, which is going to be 6.78. So it comes out to be 6.708, the value of this. So now we have everything. We incorporate this into the equation for electric flux density. So the electric flux density comes out to be rho is equal to 20 into 10 raised to power minus 3 divided by 2 into 3.14 for the value of pi, and then the value of rho, which is the absolute, is multiplied by 6.708, and then you have the unit vector, which is going to be minus 3ay plus 6az divided by 6.708. 6.708. So now the answer comes out to be minus 212 a of y plus 424 a of z microcoulomb per meter square. So this is the electric flux density for this problem, and let us confirm the answer. It is the same as minus 212 and plus 424 a of z. Now let's come to the final part of the problem, which is part C, and now the source is a uniform surface charge density with a value of 120 microcoulomb, and this is on the plane z equals to minus 5. So the point is should be z equals to minus 5. So let us see the third part. So now the surface charge density is having a value of 120 microcoulomb per meter square, and z is having a value of, or the plane is at z equals to minus 5. This means the sheet is formed at z equals to minus 5, and we need to find the electric flux density for this sheet or surface charge distribution. So let us draw the axis and understand where the point is and where the plane is from. Since this is my z, this is my y, this is my x, I can say this is my negative z, and I can say that the sheet is, let's say, formed somewhere over here. So this is the sheet around the z equals to minus 5 meters. So this is the plane or the sheet where it is lying on z is equal to minus 5. Now where is my point? Again, my point is at 2, minus 3 and 6. So 2, minus 3 and 6, it is again somewhere over here. This is point P, 2, minus 3 and 6. Okay, and this is the sheet of charges over here at z is equal to minus 5 plane. Okay, so I need to find the electric flux density for the sheet charge distribution or surface charge distribution. So the equation is rho of s divided by 2 multiplied by the normal unit vector a of n. In this case, the value of rho s is 120 into 10 raised to power minus 6 divided by 2, and the unit vector is always where the sheet is. In this case, it is going to be a of z. Now the question is whether a of z is going to be positive or negative. How can we figure out? So in order to figure this out, we have to see where our original test point is. So it is at plus 6 and the sheet is at minus 5. This means the energy of the charges will move from point sheet z towards that point. So it is moving in the positive z axis. So this will always remain plus a of z. So this means my answer now comes out to be 60 microcoulomb per meter square along a of z. So this is the answer of the electric flux density that was required. We can confirm that it is also 60 along positive a of z microcoulomb per meter square. So this is the solution to the second problem. I hope you understood how to find electric flux density and the electric flux, keeping always in mind that electric flux is equal to the total charge enclosed, and electric flux density value will vary depend if it is a point charge, if it is a line charge, if it is a surface charge, or if it is even a volume charge. And we can understand this by the two examples that we did.